Thank you for tuning back into the Automation Podcast. My name is Shawn Tierney from Insights in Automation, and this week I meet up with Ivan Spronk from Siemens to learn all about their G220 clean power drive. I also want to thank Siemens for sponsoring this episode so I can bring it to you completely ad-free. So with that said, I want to welcome back to the show Ivan from Siemens to talk about VFDs. And this is something we've been wanting to talk about for a while. But before you jump into your presentation, Ivan, could you introduce yourself to our audience for those who maybe didn't catch your last appearance?
Thanks a lot for just having me back to the show here. I got a slide up here that introduces myself. I'm the product manager for the SINAMICS variable frequency drives for Siemens here in the US. So yeah, happy to be back on your show. And what I would like to talk to you about and discuss with you is our latest variable frequency drive. It's the G220 and specifically the clean power drive. This is a best-in-class solution for a grid-friendly power quality when using variable frequency drives. So Shawn, you audience may be wondering why we should discuss power grids and variable frequency drives, but I'll just say, if you've been around variable frequency drives or VFDs, as I'll refer to them, you've likely had conversations or heard something about VFDs creating or generating harmonics on the power grid.
Oh, yeah.
Yeah. Or maybe someone in the audience has been involved in a situation where harmonic current and associated voltage distortion on your plant's electrical grid were causing overheating on transformers and cabling, or potentially causing circuit breakers to trip there, fuses to open. Or maybe you're just an engineer looking to select and specify a variable frequency drive, and you may need to answer some questions about harmonics that typical VFDs generate. You can relate to any of those, or if you're just interested to know more about this topic, we'll invite you to stay tuned here for the next 35 to 40 minutes for a discussion on power quality and VFDs. So, Shawn, I'd like to just ask you, have you heard anything about the power grid lately?
Well, yes, I've heard lots about the power grid. I know that this is more and more becoming a big issue because when you have a lot of VFDs producing all kinds of harmonics, that can cause lots of problems like the ones you just mentioned. But also, the utilities are starting to see this and saying, why are we putting up with this? So, aside from the power grid needing to be hardened against all kinds of things, everything from EMPs to, Yahoos shooting transformers in the middle of nowhere. This has been, I think, a big and growing issue. That's why I'm glad that you're on to talk about this, because in the pre-show, I really got a sense of how important this was, in 2025 and going into 2026.
Lots of conversations about the grid and really how the electrical grid is being stretched. And with all of the, data centers being built, lots of conversations about how power is going to be supplied with those. In other words, I think for maybe the first time in 25 to 30 years, they're anticipating power usage and power requirements going up. So that's why I think all these utilities and plant operators are interested in the grid. So some reasons to discuss then the power grid and variable frequency drives is variable frequency drives, very useful for motor control, but left unchecked, they can introduce several power quality issues. Harmonics, as you can see on the screen here, typical VFDs use rectifiers that generate nonlinear currents that also distort the voltage waveform. And these harmonics can propagate through the electrical grid. And, with that voltage waveform potentially affecting other equipment or, at worst case, other utility customers. These voltage fluctuations can lead to flicker in lighting and perhaps even take other sensitive devices offline. Typical VFDs, some of them can negatively impact power factor. Again, something that's of interest to utilities and plant operators. And just, there could be some resonant frequencies set up that may interfere with other things. So those are all things that, harmonics and, the voltage fluctuation, things that are unfavorable, I'll say. And what I'd like to do here, Shawn, is just kind of introduce, what I want to tell you is we have a very unique product here in the SINAMICS G220 clean power drive. three advantages of this product we'll want to talk about here through the course of this podcast. One is the clean power technology. So you can see total harmonic current distortion is well under the strictest harmonic standards there at less than 2%. It delivers near unity power factor under almost any load conditions. And I'll just say, there has been technologies out there that have been able to produce, those two attributes of low current harmonic distortion and near unity power factor. But what's most unique about this product that we're launching here is the compact space-saving design, and it is the smallest low harmonics drive in the market. And also available, it's all self-contained, so there's nothing extra to install. It's all in one footprint. And I'll give you an example here. This product is released up to through 150 horsepower now. By the end of the year, we'll have it released up through 200 horsepower. So this is a relatively new product on the market. But that 200 horsepower drive, imagine this, Shawn, less than 3 feet tall, less than 12 inches wide, and about 14 inches deep. That's a 200 horsepower drive that will guarantee these things I've got here with low distortion and near unity power factor.
That's not something I would have thought of, is that these clean power drives are typically larger than their standard cousins. And so the fact that you've been able to get these smaller and closer to the size of the standard drive is pretty impressive.
We'd like to think so. Let's dig into, first of all, if, I said variable frequency drives or typical frequency drives can generate harmonics. So why would people want to use VFDs? Turns out variable frequency drives are really good at two things. One, saving energy, and two, improving processes. So just, kind of as a reminder, why do people want to use variable frequency drives? Just a reminder, half the world's electricity is used by motors operating pumps and fans and compressors. And just as a reminder, Shawn, if you've got a 20 horsepower motor operating, and I just use 12 hours a day, 265 days a year, I used average commercial power rate of 12 cents a kilowatt hour. That electric motor is going to cost you running across the line around $5,500. If I operate that motor with a VFD and I've got opportunity to adjust the speed, based on demand, electricity cost is half of that. So $2,500. And that even gets more grows, your savings grow if I consider a 100 horsepower motor operating 12 hours a day, 250 days a year, again, with that same kilowatt hour. That running that electric motor across the line is going to cost you, I've got on the screen here, $28,000. If I've got the opportunity to adjust speed and control speed as I do with the VFD, and the application can, of course, doesn't have to be run at full speed, just typical savings, again, it's going to cost you less than half to run that electric motor. So I like to put those numbers in front of people, Shawn, because I think people lose sight of how much it costs to run an electric motor. So any thoughts on that?
Yeah, when I first got in this industry back in 90, this was big. This was talked about all the time. They were like,
Sure.
if you get a fan or pump and you don't have a VFD on it, you're just wasting money. And to some extent too, soft starters. But the point being that, if the way you drove your car was you just put the pedal to the metal everywhere you went, you could just realize that's not going to be very efficient, fuel wise. And so, putting aside the process thing, because many processes you can't just do a cross line starter, right? It would be great for the process, but typically fans and pumps, I mean, the amount of savings is tremendous. And I know for a very long time, this was, it was up there with lighting, upgrading your lighting in your plant.
Sure.
Just installing VFDs or upgrading VFDs from very old VFDs. A lot of times the cost savings and the rebates would make the project pay for itself within a year or two, if not sooner.
Sure.
So it's for anybody listening, I know all the old timers out there are like, yeah, know all about this, but if anybody's listening and you haven't taken a look at that, definitely call your local representative and ask them about energy savings with VFDs, because it's huge. I mean, it's just massive. As you show in this slide, but it's super. Now, at your second point, processes, yeah, some processes, I mean, they wouldn't be possible if all you had was across the line. We think about needing a very precise control, very precise movement, maybe not servo control, but in some cases, just you know, starting the VFD across the line would break things, right? You need to coast
Sure.
up and coast down, and be able to vary the speed based on the what product you're making sometimes. But let me turn it back to you.
Sure. So one of the links that I've got in my resources is a link to, it's called SinaSave. It's just our Siemens name for our energy savings calculator. So somebody, with that link, somebody could go in there and very quickly, put in their own horsepowers and speed profiles and energy costs and see for themselves, more dialed in. So yeah, and I liked your conversation about the process. I mean, so I think what I'm trying to establish on this slide really is PFDs are very useful and very effective at helping manage costs and improve process. So, VFDs are not going away. So now let's then dive into figuring out, okay, how do we handle harmonics that typical drives generate? So first, Shawn, let's start with a conversation about what are line harmonics. And I've just got a few slides here to talk about that, but we'll relate it to, what we call linear loads, which is like an induction motor or resistors or incandescent lamps. They draw sinusoidal or linear current proportional to voltage. So in other words, for the audience looking at this slide here, you can see very nice looking sine waves. Yeah, in this country, of course, that's coming from our power plants at 60 hertz. Looks very nice, right? Well, when you put a nonlinear load on your electrical distribution center system, yeah, and nonlinear loads are any power electronic device that's converting AC power to DC power. So that's what we're doing in a VFD. We're converting AC power to DC power, but also computers, that's obviously not the same, talking in the same magnitude of power, but this is what computers are doing. Same thing with LED lamps now, discharge lighting. And very interestingly enough, this is also what's going on in EV charging stations. You're converting AC power to DC power, so that's considered a nonlinear load. And what happens there in a nonlinear load is it doesn't draw, it just draws power in pulses when the capacitors need to charge. So think about these capacitors charging more at the top of the waveform. And that's then what causes these variations in both voltage and current from the fundamental sine wave. And, in very simple terms, that's what these harmonics are. Yeah, they're non-sinusoidal, they're non-linear, impedance is changing with the applied voltage. So there's some things that they, negative impacts, we'll say. And again, for the audience that's looking at the slide there, you can kind of see some of these nonlinear currents stacked up there. Point is, it creates a much more complex waveform, and there's current flowing at those multiple frequencies. So Shawn, I've got, for people that are maybe having a hard time visualizing this, I've got a little example. So can you think, Shawn, of a musical group that sings in parts?
Mm-hmm.
Even if we can't mention them on the air, we can all think of, a group that sings in.
Yep.
Yeah, exactly. So here we go. We've got a musical group singing in different parts, and these different musical parts are sung at different pitches or frequencies, and that all blends together to make a richer sound, right? Well, we can think of that fuller sound that's flowing at those frequencies. That's kind of like more current flowing in there. So, back to our harmonics example. So, yeah, there's current flowing at these other frequencies other than 60 hertz, and that kind of fundamentally becomes a problem we need to deal with. Yeah, and then in that group, Shawn, can you think of someone? What does it sound like when they sing off key?
Absolutely.
It doesn't sound good, does it? So maybe we'll think of that as voltage distortion. So we gotta do something about that too. So
yeah, I like to, for me, and I think the charts, for those listening, I think the charts really spell it out. They're color coded and they show the different harmonics. And for me, I think charting it is kind of one of the ways to understand it visually, because if you think about let's say you have a large rock, a medium rock, and a small rock, and you throw all three at the same time into a pond. You can visually see the big ripple, the medium ripple, and the small ripple, but it's really hard for you to understand as they're spreading out what the effect would be on, any, maybe toy boats that your kids have in the water or grandkids have in the water, right? And
Yeah.
so it's a very tough for human beings to try to keep in their head more than three things happening at a time, right?
Yeah.
I love seeing the chart here, and it shows the relationship to when the capacitors are charging and how that affects the primary and the sympathetic and then different waveforms. And I just know that these are, inducing currents, and each one of these are inducing currents, but it's like that throwing multiple rocks into a
Yeah.
body of water. I just can't. I need to see it. I need to draw it out. I just can't, understand. Hey, well, that means this little boat's going to go to the northwest because, and this is where I think it's easy to overlook the effects that these harmonics have because it does get kind of complicated to visualize.
Yeah, no, I like that analogy of the rocks in the water too. You can see those waveforms, and yeah, it becomes more current flow that has to be dealt with, and the voltage notching is something. Again, talking about typical VFDs. I've got a little picture here of showing in the center of the screen there, just main section of a typical VFD with the rectifier front end. That's a 6 pulse standard 6 pulse rectifier in there. That's what is very, very common. You can see the DC link capacitors in the middle there. And of course, the inverter section on the output, which is recreating that sine wave. But let's turn our attention to, the input waveform that we're showing. You can see, drawing power, creating that notched waveform. And really what I want to point out on this slide is, okay, that's kind of at the top of the slide. I've got a picture of one drive doing that, but, on any given distribution system, there's a variety of loads, right? Each with its own signature that interacts with each other. So you end up in trying to show down in the orange section here of this drawing, okay, all of these different loads combine with their own signature to create kind of a system signature, if you will. And then what happens is, okay, you've got standards that we'll talk about here a little bit, but standards and specifications, you'll see if you're an engineer dealing with harmonics, they often refer to this point of common coupling. So that's kind of what I'm trying to come across on this slide here, as well as when you have a system, it's very useful to identify this point of common coupling where you're going to measure these harmonics. So you'll see that in a lot of specifications. Not sure if you've ever seen that, Shawn.
No, and just the point of common coupling, when you're saying that, you're referring to, go ahead, give me that again. What does that actually mean?
If you notice over on the right side here, we've got a different loads. I'm showing a couple of different drives. I'm showing a few motors operating across the line, each with their own signature, but that ends up creating, on the distribution system, a system signature. So we need some place, to decide, if you're trying to meet a spec, well, tell me then where I have to measure it. So that's what this point of common coupling is. And I just wanted to get that term out there because people have often heard of this. Sometimes it's right at we'll say connection to the utility transformer. If you're a plant operator, maybe you've got a handful of buildings over here and you want to define a point of common coupling between some of these other buildings.
Mhm.
But it's just a place to define for a measurement.
So in this case, let's say they have a transformer here. This transformer feeds two, let's say VFDs and then two motor starters. So there's
Exactly.
at that point, on the outfeed of the transformer, which we know we have four loads on, to be that point of common coupling. Because what's going to happen is we have all these different loads, so we have all these different waveforms, we have the different harmonics from the VFDs. So that's going to average together to give us a waveform. That's the combination of those four devices. And that's
Right.
point of common coupling. All right, I'm with you. Thank you.
Exactly. Yeah. Again, just one other factor, just to talk about a factor that impacts the magnitude of harmonics, is something else you'll see in a lot of specifications is what's called the relative short circuit ratio. And really, this is just a metric that's used when evaluating the grid's ability to support variable frequency drives and really any other nonlinear load, which, we mentioned LED lighting, and there's other nonlinear loads out there too. But what it does is compares the strength of the grid or distribution system maybe that you have in your plant to the size of the connected load. And of course, this ratio and therefore the magnitude of the harmonics is impacted by transformer size, by what you all got connected, if I've got other reactors, how much cable I've got connected, and then probably most importantly, by load size and type. In other words, by load size, I mean, okay, is this 50 horsepower or 200 horsepower? And by type, meaning, is this 200 horsepower running across the line, or is it with a VFD? I'd like to give an example there, Shawn. Water treatment facilities, often you hear a lot about harmonics in those facilities because often there's such big motor loads being controlled by VFDs, and that is by far the largest, represents the largest percentage of load on that transformer, right? So I've got to imagine kind of this remote water treatment facility, what's out there, probably 4 to 5 to 6, depending on how big it is, huge motors running pumps, right? And not much else. So there's an example of people that would be, very concerned about how much, what percentage of nonlinear load do I have on my transformer? So that's kind of all relates back to this short circuit ratio. Again, something you see in a lot of specs. So just trying to give some definition around what that is. Sure, if you got any questions or anything you wanted to add or.
No, I appreciate that. Appreciate you going over.
No, kind of the point I'm trying to make is, there's multiple factors that impact the magnitude and lots of things to think about and figure out. It's like, wow, if you're a plant engineer with responsibilities for a power grid, wouldn't it be great not to have to think about this? And I guess ask you to remember, what I showed you at the beginning of this is, wow, our product, take that, whatever I drive is giving you no distortion at the terminals, no, near unity power factor. So it becomes something that can really simplify, make a life of a plant engineer much simpler by specifying products that are, low harmonic content. So let's talk okay, so we kind of defined variable frequency drives. We like them. They do a lot of good things, but okay, there's some things going on with harmonics. Okay, so what's necessarily bad about these harmonics? So I've got a couple of slides here showing that'll walk us through the effects of, kind of the pain points of harmonics. So, with regards to transformers, generally, remember we talked about there's more current flowing at these other frequencies. So that's going to induce some additional heating and additional losses, likely to see some insulation stress, possibly even some resonant frequencies that are going to set up core vibrations. So those are some of the, undesirable things with generators. There's most good-sized facilities have a standby generator, right? Well, now if I'm operating a lot of nonlinear loads, I'd really start to need to start to pay attention to, okay, is my generator going to work to power these nonlinear loads? So something to consider there. And what ends up happening is people may have to oversize that generator to be able to run these nonlinear loads. And dropping down to cables and conductors, again, if I've got more current flowing through them, that's going to increase your cable losses due to increased cable resistance caused by the skin effect, which is something that in tendency of alternating currents to flow primarily along the surface of the conductor, increasing or decreasing its ability to, do its job and really deteriorating the insulation due to excessive heating. So those are all, negative things that happen when you have a lot of harmonics, right? All right, looking at one more slide of just some, negative impact on circuit breakers or that may trip prematurely or fuses that may open prematurely. Again, thermomagnetic circuit breakers have these bimetallic strips that may be impacted by those additional currents flowing. electronic type circuit breakers use current sensors, which need to account for, these harmonic currents. Yeah, most circuit breakers are designed to trip at a zero crossover point. So with these distorted currents, there may be some spurious zero crossovers. And then kind of some similar problems with fuses, again, due to heating effect, this RMS current and non-uniform current distribution through the fuse element. What tends to happen is people may have to oversize fuses. But of course, I'm also, to match that actual RMS current that's flowing with these harmonics. But okay, that's not necessarily, unless somebody's out there measuring it, they don't know what that is, right, Shawn? And I've got codes to meet. I can't just put a way bigger fuse in. So, it kind of becomes this balancing act, right?
Yep.
So, so those are all things, that happen when you have a lot of harmonics. Again, I can kind of summarize them on one slide here. Line harmonics produced by these nonlinear loads cause overheating, inefficient operation, and more losses, perhaps some premature line tripping, perhaps some system oscillations and instability, perhaps noise, and reduced power factor. So none of those are good, right? In general, reduced efficiency, increased power loss and energy costs, and of course, then higher carbon emissions as well. And yeah, to kind of summarize this all up, current distortion is bad, infects all your systems. You got to account for it. Voltage distortion is often the one that will get people. That's much worse because that goes all other systems as well if left unchecked. So that's my summary slide there of effects of harmonics and why we want to do things to control them. So any thoughts or questions there, Shawn?
No, I think the slide does a good job of showing that, this is not just for your VFD, VSD. It's the other things on the line too that you're affecting, right? So, I'm
Absolutely.
sure some of those listening or watching have stories of where one drive, two drive wasn't a problem, four, five, six drives, and they started seeing these issues because it was cumulative, right? The more drives you have. So, I'd love to hear any stories you guys that are listening and watching have about this and what you did to resolve it. But
Sure.
this is, I mean, in some cases, you may just need to get a VFD like this clean power drive that eliminates this problem versus, other ways of dealing with it.
Sure. Oh, so yeah, that leads well into my next kind of couple of slides here. I mean, harmonics are not new. Line harmonics voltage distortion isn't something that's new. I mean, this has been around for as long as VFDs has been around. So people have come up with, ways to mitigate this. And I've got, 5 of those methods listed on the screen, and we're just going to kind of very quickly step through these. But the last one there is really, we're going to get to, okay, what is in the G220 that makes it unique and why do I want to talk about it? So again, and we'll come back to this summary slide at the end here, but just, okay, like I said, people have come up with a handful of different ways to try and mitigate harmonics. First one is just, a simple line reactor. And what you also see is some manufacturers, and Siemens has done this too, to some of our lines. We have DC chokes in the, in that DC link section. It's an inductor, and really all that's doing is opposing rather the rate of change of current flowing through it. So it kind of takes the top off of those notches, if you will. Yeah, it's simple, probably economical. It's usually applied to each VFD. If you know something about what impedance you need, there's a selection, available in these AC line reactors. You can select the impedance you want, but some of the negative things is they take up more panel space. They got a wire, and in reality, it only offers kind of a small improvement. So people invented other things. So the next thing I got here is people came up with, they call them passive harmonic filters. They're also called line harmonic filters, LHF, you see that, or harmonic trap filters. And what these do is they eliminate or control kind of those dominant lower order harmonics. I didn't talk about this much, but these harmonic currents that are flowing, they're much more dominant kind of at the lower end of the frequency range. So these harmonic trap filters work on, those low order harmonics, and they can be effective for, putting in front of a drive. Kind of what they consist of is a LC circuit there, maybe with a damping resistor, and they get tuned to these specific frequencies. So, but again, it's a device that takes up panel space. I have to install that separate from the drive, so I got to wire it. And then they don't do a very good job because they still have voltage notching and instability on generator operation is a known problem with these things. And okay, you're introducing more losses to the system. So that's passive harmonic filters. The next thing I've got here is you may have this has been pretty common in the industry. It's called the 18 pulse front end. And really what this does is takes your incoming 3-phase power and really converts it to 9 phases with a, special transformer that creates a phase shift between these different now 9 phases. So I got to have this 18 pulse diode bridge, and you can kind of see that on the slide here too. So I need, this involves a lot of equipment. I need this auto transformer. I need a different rectifier bridge, a much bigger one really, but it does do a really good job of, so I'm not drawing current in big chunks anymore. I'm drawing current more often, right? Because I've got this, 18 pulse rectifier. So it really does a good job of meeting, there's a standard out there called IEEE 519 that's referenced that we'll talk about just a little bit more here in a bit. And these also work relatively well with a standby generator. Some of the negative things is, okay, as soon as I introduce that transformer and more switching, that reduces my system efficiency. And really the big one is this takes a ton of space to not only mount that transformer, but that 18 pulse rectifier. I got a wire between all of that. So it ends up being a pretty substantial product cost in terms of component cost and floor space cost. So, but, has been widely used in the industry, but a lot of metal, copper and iron being used in that solution. Next one here is just active harmonic filters. And again, this really is something that uses an IGBT bridge and a DC bus, much like the front 2 parts of that AC drive that I showed you. So we've got kind of the front end and a DC bus sitting there. And what this really does is monitors the current and then really generates compensation current in opposite phase to offset harmonics. So this can be, effective. The waveform looks pretty good. It's unaffected by impedance changes because it's managing the switches. But yeah, it tends to be, more complex. It's more expensive than passive filters. And again, it becomes another device to install. Commissioning can be a bit of a challenge because you got to get this tuned to obtain optimal performance. Although there are some self-tuning ones out there that, help take that burden away. But yeah, you got to install another piece of equipment that takes up, think of it as, it's 2/3 of another VFD sitting out there, right?
I would think it is also less energy efficient too, because so we all know we have noise canceling headphones. They take
Yeah.
power to generate a canceling waveform, right? So we were already losing power because of the harmonics, and now we're generating another waveform to
Yeah.
cancel out the harmonics. So it just seems like we're losing more energy to produce this canceling wave. So I mean, I could if this is the option that works, and you have the space, granted, but it seems like it's less energy efficient than maybe a passive filter, right? But I don't know. What do you? I mean, 2/3 more of the panel space as just the VFD alone. That sounds like a lot of equipment.
Give you a good looking waveform. So I think that's why people like it. But yeah, it is definitely something that's more complex. And again, I think also there's that commissioning aspect. And another thing is, okay, so you get it set up on a given distribution system and it's doing great. Okay, what happens when I add a couple of more drives on this distribution system? It's going to change the dynamics and may need to do some recommissioning. So again, it's something that a plant operator would need to, pay attention to. So all of those methods, and what I'm going to get to next is something that's actually in the G220. So all these previous methods, kind of worked to a degree, and each kind of has its maybe strong points and not so strong points. But what I want to talk about now is something that's called active front end. And this is, the G220 Clean Power Drive is a version of this active front end. So active front ends, so what do we mean by that? Basically, it's, a sinusoidal input rectifier, and we are controlling the commutation or when we're conducting energy. So with that, we can get, if done right, we can have a high dynamic response. So we can respond to changes, for instance, in voltage dips in the distribution distribution system. And because of that, then we can also kind of get, because we're controlling when we're conducting current, it's near unity power factor. So yeah, these active front ends, there have been versions of these drives out there as well. What's unique about the G220 is that it's a 2-quadrant active front end. So power is flowing only in one direction. So in other words, from the supply or line source, through the drive to the motor. These are called clean power. So you hear the name clean power in feed. That's because, okay, the in feed or line supply is clean. This is known as something out in the industry. They're called Vienna bridge rectifiers. Vienna bridge rectifiers, something that was invented in the mid 90s. And basically, I just put up a bigger diagram of kind of what's going on here. There you can kind of see, okay, it is only 2-quadrant, but there's this 3-level switching process that really reduces all these lower ordered harmonics. So this provides then a stable, controllable. The advantage is high voltage DC output, so there's no voltage reduction going on. Makes it ideal for high power applications like VFDs. And again, remember I mentioned earlier in the conversation here, electric vehicle chargers. So this is a technology that's been popularized by some of the people, making electric vehicle chargers as well. So, and really, what we're doing here is using on smaller sizes MOSFETs, or on larger sizes, IGBTs here in the power section. Mm-hmm. And then using a very, part of the sauce here is the control or of the pulse width modulation to manage power inflow is really as short a sentence as I can come up to describe what's going on here. With this, because we're only controlling power in one direction, there's some ability, we don't have as many switching losses. Again, because we're only dealing with 2 quadrants, it's a compact size, but it is non-regenerative. And I just, what I'll do here is I'll put up, a 4-quadrant comparison. So there are active front ends out there that are 4-quadrant, which has more of a full IGBT, front end to it. The advantage of that is you do get power flow. It is regenerative. You do get power flow in both directions. But of course, now I have higher losses because I'm switching in both directions and just a little bit less efficient. So really kind of coming back to what's in the G220 clean power drive is this 2-quadrant Vienna bridge rectifier. Again, because we're only controlling power in one direction, there's some space savings that come from that. So and I'll just add 2-quadrant. So that's why this is targeted at non-regenerative load applications like pumps and fans, right, and compressors. Those are not regen load applications. If you need something 4-quadrant, that would be like think of a hoisting application or something like that. Maybe large centrifuges or something like that has a lot of mass that's been accelerated up and can capture some regen on the decel. But that's kind of what's in the G220 clean power drive. So Shawn, I'll just kind of stop there. And by the way, the waveform is fantastic. Just dialed that in there. So any thoughts or questions or what's on your mind there?
Yeah, no, that's important to know. So, you got the 2-quadrant. version in the Clean Power G220. And the important thing here is you're going to get beautiful elimination of harmonics. You're going to have a beautiful waveform. But when you make this choice, you're also opting out of regen, like you said, like a hoist or a large inertial load. There'll be no regenning, which in some
Exactly.
cases you'd be choosing a different VFD. That's just a different application, right?
Exactly. Yeah.
But I think most VFD applications, at least the ones I've seen over the years, do not have any regen, right? They're
Yeah.
your standard purpose, even your high performance VFDs are not doing regen or anything, any type of regeneration capabilities. So I think for most applications that's not going to be an issue, but it's important to point out.
What do you think? Some people we've asked questions. Well, why didn't you just make it 4 quadrant? Well, let me ask you, Shawn. What do you think's less expensive to make, a 2 quadrant or 4 quadrant version?
I got a feeling the 4 quadrant may be twice as much.
Yeah.
Well, at least that part of it, right? The front end.
And what do you think would take up more handle space, a 2 quadrant or a 4 quadrant?
Yeah, exactly. Exactly. Yeah.
So, I mean, it's a very targeted, again, targeted at those applications that are non-regen load applications, which, yeah, I'll submit that's at least 80% of what's out there. So again, this really just to emphasize, it's a Vienna bridge rectifier, so some uniqueness there, but then really also the software side of it, building the algorithm to manage that power flow and assure efficient operation is what's been done in the G220 drive. And yeah, with regards to nice looking waveforms, it's lights out, the best looking waveform out there. And matter of fact, I've got one more slide here that shows just, development team took one of our G220 products, so this is what's shown over on the left side here is just your standard power, waveform. You can see kind of the double hump waveform there. If you put a passive harmonic filter in front of the G220, waveform starts to look pretty good. But now if you just use a clean power drive, you get a very nice looking waveform. All that worrying about what the effective harmonics, how they're generated, you don't have to think about that anymore, because right at the input terminals of the drive, we're giving you very, very low turned harmonic distortion. So, and also that near unity power factor. So that's really the advantages of the clean power drive.
Well, and just for the audio audience, I mean, we're looking at the standard G220, right? Your standard drive. You're looking at a total harmonic distortion of, let's say, 33%. Well, you put that passive harmonic filter on, that standard drive, now we're down to around 4%, right? But if you have a lot of those drives, that may not be enough, right? So with the clean power G220, we're down to under 2%, 1.9% total harmonic distortion. And you see that, I know you guys listening can't see it, but you can see that in the waveforms. All the
Yeah.
viewers who are watching can see the waveforms, definitely the improvement as you go through each of these options. And again, you'll know if you need clean power. I'm fairly sure that, if you don't need clean power, you don't need it, right? But if you need it,
Right.
and this is something that I think we'll see more and more because, quite honestly, I mean, power factor, we all know how that affects your utility bill and what the
Absolutely.
power company thinks about that. And so we can expect more stringent controls over time as, yes, the systems become more advanced. You're going to get dinged if you have really bad power, the quality of the power. If you're causing problems down, for the rest of the block or for the rest of the business park, they're going to start tracking that. So let me turn it back to you, Ivan.
Yeah, we're kind of to the end. I've got a couple of slides just to summarize what we've talked about here. The G220 is, yeah, a new drive for us. It's our next generation SINAMICS product. And really, this drive was designed and built on 4 pillars of digitalization. So in the form of, having a digital twin capability to help engineers shorten design and engineering efforts when sizing a drive system, and then tools to optimize operation once it's up and running. And you can see another pillar of secure, meaning security with regards to cybersecurity and safety that protects people from machines and protects machines from people as well and other sinister actors. And ease of use, next generation product, starting with a clean sheet of paper. Okay, some things were done with regards to selection, configuring, commissioning, training, things like that, with making the product as easy to use as possible. And then this fourth pillar of being sustainable, optimizing manufacturing resources and materials used, even operational efficiency during the life of the product, and then even considering, the end of the product life cycle. So all of those things designed into the SINAMICS G220. And then if we look again specifically at the advantages of the clean power drive, that nice clean low total distortion that complies with the harmonic standards, near unity power factor, and again in that space saving design. And just to kind of give you an idea, I've been telling you it's small, and I think I maybe let the cat out of the bag at the beginning of the presentation as well. Yeah, here's kind of a table that shows dimensions, and there's that 200 horsepower drive that I referenced. So yeah, this technology, it's not like buy the drive and buy something else to add on to it. It's all in one package. And yeah, that 200 horsepower drive, 31 inches tall, less than 12 inches wide, and about 14 inches deep. That's a 200 horsepower clean power drive that would, yeah, you wouldn't have to think about all this harmonic stuff. And I'm not going to put up a chart that shows competitor A, B, and C and our product next to it, but you can take that table and go look at other people's solutions, and you'll see, yeah, it's a very compact device. So that's kind of the point of that slide there, Shawn. And yeah, really my last slide then, just kind of, I have drawn heavily from a white paper that my counterpart Nikunj Shah wrote. So we'll give you a link to go download that white paper. That discusses a little bit more. I've kind of mentioned on and off IEEE 519. That is by far the prevalent standard in this country for, describing what harmonics are, different mitigation techniques. And then, there's tables in there is like, okay, if you're being called to meet specification IEEE 519, here are the harmonic current distortion levels and voltage distortion levels that you need to meet. So that's all laid out in that white paper. Yeah, and then we'll give you a link to our website, to the G220 catalog. I have another very useful feature showing that I'll give you a link to is the Siemens product selector, where you can go and, put in a part, very quickly pick a part number and then get to some, CAD models of it. And then I've mentioned that energy savings calculator and all. So Shawn, that's kind of what I had for today. I hope that was interesting to you and more importantly, interesting to your audience.
Yeah, and I just want to remind the audience that we had you on to talk about the G220 a while back. We also had Jackie on to go through commissioning the 120 and the 220. So if you're kind of curious, how do you do that in TIA Portal? Because I'd never done that before. So Jackie came on and she walked us through that for both of these two models. We also have received some samples from Siemens. So we will be trying those out ourselves here in the studio. Don't have a date on that. We're a little backed up here, but definitely they're right in front of me every day, so I don't forget about them. So we'll be doing that as well. And then we'll make those available to our in-person students who come to the school, as well as we'll add those as lessons to the online course over at the Automation School. But so lots of stuff. We've had a lot of coverage. If you have any questions, check out this white paper. I'm sure we just touched the surface of what's in there. And of course, Ivan and all his colleagues at Siemens would love to hear from you. And Ivan, let me pass it back to you for the final word.
Yeah, just thank you so much for having me on, Shawn.
Well, I hope you enjoyed that episode. I want to thank Ivan for coming on the show and giving us that very technical presentation, which I totally enjoyed. I hope you guys did too. I also want to thank Siemens for sponsoring this episode, because you guys know I love to release them completely ad-free and available to the entire public. So with that said, I also want to thank you for tuning back in this week. If you think about it, please give me a thumbs up or a like or a 5-star review. That is the best way for me to find new vendors to come on the show. And with the exception of Thanksgiving week, we should have a show every week up until the last 2 weeks of the year. And we are already recording shows for next year. So I'm excited about that. If you know any vendors you think we should be on the show, please reach out to them. I'm working on a new media guide as well. And so we'd love to have them on the show this coming year of 2026. So with that said, I just want to wish you all good health and happiness. And until next time, my friends, peace.